Today's problem is going to be permutation string. In this problem, we're going to be given two strings s1 and s2, and our job is to return true if s2 contains a permutation of s1, otherwise we return false. And in other words, if a permutation of s1 exists as a substring of s2, then return true. Both strings only contain lowercase characters. So in this example, we know that the output should be true because we can see a permutation of ABC in this string here, this one. And in the other example, where s2 is LECAABEE, we can't find a contiguous block of substring that is a permutation of ABC. Alright, say this is our input. So we know that the length of S1 here is 3 letters long, right? And in S2, why don't we just test every contiguous 3-letter block to see if that 3-letter block is a valid permutation of S1. Okay, so let's give that a go. So we'll test the first 3-letter block here, LEC. Is LEC a valid permutation of ABC? Well, the easiest way to check this is probably to turn this into a dictionary, right? So if I have A equals 1, B 1, and C 1, the value is the number of times the letter has appeared in S1. And we also turn this into its own dictionary. L appears 1 time, E appears once, and C appears once, right? And since dictionaries have no concept of order, which is what we want, we can just compare these, right? So if they contain the same letters and the same number of letters, then it must be that they are permutations of each other. And in this case, it's clearly not the case, right? So let's move on. Let's check the next 3-letter block here. ECA. So we got 1 E, 1 C, and 1 A, right? We got rid of the L, and now we have an A. What about now? Well, still not the case. It still doesn't match up. Next one, we don't have an E anymore, and now we have 2 A's. This does not match. What about now? We have 2 A's, 1 B. This does not match. And for the final block, it's ABC. We lost an A, but we got a C in return, and this matches. This is probably the simplest solution that we can have, and it's really not bad. And if you were to code it, it's going to be something like this. We're going to first define L and R, and this is going to mark the start and end of our window, right? So L is going to be the first letter of S2 here, which is L, and R is going to be the C here, right? And once that's done, we can create our S1 counter. This is the target that we're trying to reach. And after that, it's as simple as looping through every substring in S2. Have a loop here. We create a counter dictionary of that substring. And then we check. If the window matches the counter of S1, then we return true. We found a valid permutation, right? Otherwise, we just increment R and L together. And if you make it to the end and we didn't find anything, we return false. And that's really it. And as for the time complexity, creating this S1 counter is going to be O of n. That's this line here. And then we're going to do a while loop over the entirety of S2. So it's going to be plus O of n times the price of creating a counter dictionary, basically at the size of S1. That's going to cost us m time, right? So we'll be looping n times, and the cost of creating one of these is m, right? So the cost is n times m. The rest of these operations are O of 1 operations, right? So this will be our overall time complexity, which kind of summarizes to O of n times m. And as for the space complexity, well, and this counter here specifically can go as large as the number of unique elements in S1, right? But since we know that the strings only contain lowercase characters, that means that the size of these counters are bounded to 26 letters, right? A to Z. So we have to maintain 2 of that, which is 2 times 26, O of 52, which is basically just O of 1. And that's a simple solution. So the next optimization that we're going to try is to try and get rid of this n times m, right? Because we're creating a new dictionary every single time. I want to use sliding window to dynamically shrink and expand our window every iteration. And I think that's going to save us quite a lot of time. And we go back to the beginning here, to the very first substring, which is LEC. So the beginning is still the same. We still initialize these. But what's different is, upon checking these two dictionaries and realizing that they're not a match, and we want to move on to the next iteration, we're actually first going to shrink it and get rid of this L. L will be 0 here. And since it's 0, we can erase this from our dictionary. And then we're going to expand it. We'll add this A to our dictionary, right? So basically, instead of creating a new dictionary every single iteration, we're actually just going to grow and shrink our array like this, while maintaining the same dictionary. And if we can do this, then our time complexity should narrow down to just O of n. Let me finish this one up. And there you go. All right, let's go back to our code here. So we're starting off by initializing the S1 counter and the S2 counter as well. And the S2 counter is going to start at index 0 and end at the length of S1. Well, if we get lucky, then we would have found a matching substring in our very first try. So if that's the case, then we just return true. Otherwise, I'm going to write a while loop. So if we can't find the permutation, then we have to shrink our window and we have to grow our window. And after shrinking and growing, we do another check to see if the new window that we've just created matches or not. If it matches, great. If it doesn't match, we do the loop again. So let's have a look at the code for the shrink. I'm going to make a variable called c, which is just going to be the very first character right now, right? So we want to get rid of that. So we'll reduce the count in the counters dictionary. And if we reduced it to 0, then we'll simply delete it and move our L up by 1. So then our window is going to be EC now, and then our S2 counter reflects that change properly. And then we extend. We moved R by 1 unit, so R before was in C, and now it's in A. And then I'm going to save that new character that we just got into a variable called C once again. And then I'm just going to increment that value. And if we don't have a value yet, the default value is going to be 0. And once that's done, we have successfully shrunk and grown our window by 1 unit, and we'll check if we got it. If we don't got it, then we'll do it again. And if we went through every single sublist and we still can't find it, then we return false. One thing to note here is that there's actually a bug in the exit condition. I'll show you why that's a bug. But for that, I have to change S2 a little bit. So let's say S2 is like this, and we'll never find an answer, right? So what happens to our code? The first 3 substrings is going to be LEC, and that's not the permutation that we want. Then we check ECA, that's not permutation that we want. We move the L and R again to CAB, and now our R is in this unit, right? This condition still fulfills. We check this and it doesn't work. And then we'll check our next subarray and then we fail to find it, right? But because we set it to R is less than length of S2, it doesn't actually stop here. Right now, R is equal to the length of S2 minus 1, right? Even after we've checked the final substring. So that means this loop's gonna run again. It's gonna shrink and we'll have BD and then it'll grow and then R will try to access something out of bounds and that's gonna crash our system. So because of that, we do need a -1 here. As for the time complexity, creating this counter still costs O of m. Creating this counter also costs O of m. So we have O of 2m plus looping through the entirety of S2. And this loop is actually going to execute n minus m times. And in each iteration, we're reducing a value in a dictionary, deleting a value. All of these are O of 1 operations, right? And in this line, when we check both the dictionaries, we know that the size of the dictionary is bounded by 26. So each loop, we will have to pay the price for this comparison, which is 26, right? Technically, we have 1 here as well. So creating this is 2m, running this is 26. And then we're going to run this loop n minus m times. And for each one, we have to do this comparison, which is O of 26. So this will be our time complexity. And if I shrink everything down, it'll just be like this. N minus m is basically just linear. So I'm just going to call it 26n just for it to be more readable. And we can just get rid of this 26, right? So for the space complexity, we have these 2 counters. Again, space complexity is unchanged at O of 1. So with that, we've managed to get rid of the O of nm. And now it's just O of n, basically. Now there's one more optimization that you can do, and that's going to be the matches optimization. So the reason why I emphasized that 26n a lot earlier is because this next optimization gets rid of the full dictionary comparison, right? You can imagine if the dictionaries were not bounded and we can use like basically every ASCII character or whatever, then it would be non-negligible to say the least. So let's see how that works. Conceptually, it's actually not that bad. So in the beginning, after we initialize this, we want a variable called matches. And matches is going to keep track of how many keys and values are matching from both dictionaries. So in this case, we can see the only one that matches here is C, right? A doesn't match anything, B didn't match anything, and C matches this one, right? If our window had like 2 C's here, this would not count as a match, right? Because they're different. The idea is, if the number of matches that we've accumulated is the same as the length of S1 counter, so this thing, then it means that every single key here has an equivalent in the S2 substring, and not only that, all of their values are also matching, which means that it's a valid permutation, right? Yes. And the nice thing about doing it this way is that we don't have to do full dictionary comparisons anymore. When we shrink or when we extend our window, all we have to do is update our matches and check. That's all we have to do. So let me show you how this is going to work. So we initialize our matches to how many here? We have 1 thing that matches, right? So matches right now is 1. Right? And obviously because 1 is not the same as the length of this, which is 3, then that means we haven't found our permutation, right? Okay, so let's shrink. L is now 0 elements. Now we check. By shrinking our window and deleting 1 L, does that increase the number of matches with this thing? Well, actually, L is not even a part of this dictionary, so it wouldn't ever influence our matches, right? So basically it's inconsequential. We can delete that. And then next, we're going to extend it to the A here, right? We'll insert A into our dictionary, and then we'll say, hey, by inserting it into the dictionary, did that give me a match? Well, yes it did. By inserting an A into our sublist, we have matched our A's. So that's fantastic. Our number of matches went from 1 to 2, right? And you notice that we're only checking the new key that was just entered, right? We don't do full dictionary checks anymore. And so for this window, we have our number of matches is 2, which is still not equal to 3. So then we go again. We shrink the window, we reduce E to 0. E is not even part of S1, so it's inconsequential to the number of matches. We get rid of that. We grow our window, and now because we added an A, we have 2 A's now. And unfortunately, by adding a single A, our A's don't match anymore. Their count no longer matches. And so because of that, we have to lower our number of matches to 1, right? So this is still not eligible, and we keep going. We move on to check out the next substring. So we get rid of C, the count of C is 0. So then what happens? You can see that C used to be a match, right? C used to be 1, and by removing it, it goes down to 0, and it no longer matches. And because of that, our number of matches go down to 0. And then we extend. We got 1B. Thanks to the expansion, we got a B that's matching, so our matches go up by 1. And then for the last iteration, we move this window over here. We cut out a single A, so our count goes from 2 to 1. And by doing that, our A's match again. So now our number of matches is 2. And then we grow it. Oh, I forgot to remove this. And then now for the C here, we now have a C equals 1. And by adding that C, we've created a new match. And then our number of matches goes up to 3, and 3 is equal to the length of S1 counters. That means we can return true. And obviously if we make it to the end of it, and then we couldn't find a substring that fulfills this condition, then we return false. So let's get to coding. First few lines are basically the same thing. We initialize our dictionaries, but then we also need a variable called matches. And we need to initialize the number of matches that we have in our very first substring, right? So I'm going to loop through every item in S2 counter, and then for each key value pair, I'm going to check whether there's an equivalent in S1. And then I'm going to write our while loop. Again, it's with this -1 because we're going to be incrementing the R and then using it in the loop. And we have this -1 again because R is going to be incremented before use. So we're going to stop one element short. And we still have the same setup where we have to shrink the window, expand the window, and then check whether it matches. And then on the bottom here, we're going to be checking whether the number of matches matches the S1 counter. If it is, then return true. And if you go all the way and we haven't found anything, then we return false, right? So let's fill in the logic here. For the shrink window, I'm going to create a variable called C, and that's going to be the element. This should be familiar to you. I'm going to reduce the count of that. And then what's different this time is we're going to check if that character is in our S1 counter, right? If it's in, that means it's the character that we actually care about. If by shrinking our window, the counter of that character in S2 now matches S1, then we increase the number of matches by 1. So this was similar to, let's say if I had S1 that was originally, let's say like A equals 2 or something, right? And then our S2 is like A is 3 initially. And then because we shrank our window, we removed a single A, and then now they're matching. And in this case specifically, we're going to increase the matches by 1, right? Now, on the other hand, there's another case where we just made it not match, right? If this was the original state, and then by shrinking the window, we removed a single A, and now we went from matching to non-matching. And then that's a no-no, right? So we have to reduce the number of matches by 1. And of course, if originally our A was like 5 or something like that, and by reducing the A, it goes down to a 4, well, it never matched to begin with. And then by reducing it, it still doesn't match. The number of matches is unaffected if this was our state, right? And then just some final cleanup lines. If by reducing it, the value went down to 0, we can basically delete that from our dictionary and increment our L by 1. So that's the logic for shrinking the window. And for extending the window, we're going to extend our R first. I'm going to save the value of that character in C, and I'm going to increase the counter of that in our S2, right? Now, if C is an S1 counter, and if by adding that value, we made a match, then we need to increase the number of matches by 1. Otherwise, if the value was already matching, and by adding 1, it ruined the match, then we have to reduce the number of matches by 1. And after shrinking and extending, then we have a window that we can check the answer for, right? Oh, and we can't forget to put this as well. After we first initialize the 2 counter dictionaries, there's a chance that we just get the answer right then and there without having to run this loop, right? As for the time complexity, initializing both of these counters is going to take O of 2m, and then we have to run this check to initialize our matches. That's also going to cost another m, so 3m for all that. This is an ON check, that's no problem. And then we're going to be running this loop n minus m times, but I'm just going to simplify it to n, and then in each loop, all of the comparisons here are O1. So simply, our time complexity is just m plus n. As for the space complexity, not much has changed here. We still have the two counters, which go up to size 26 each. Space complexity hasn't changed. It's still O of 1, but we've just kind of optimized away the 26n from last time here. Thanks for watching. Okay, bye.